we're still slogging through the material on machine level programming, which, as I talked to you earlier, I think is in some ways the core of this course that much of the rest of the material builds upon. And hopefully you've all had a chance to check out Lab 2 and your BOM lab, and you've gotten started on that. And certainly by the time you're finished with the material from today, you will be well on the way to solving all but the last 1 or 2 stages of the BOM lab. So I highly recommend you get going on that and not put it off to the last minute. And what we're talking about today is how procedures, I'm going to use the same terminology here, whether it's a function, a procedure, or an object-oriented programming, a method. Those are all roughly the same thing, and what we'll talk about covers them overall. I'll also mention at the outset that the way this is handled in the procedures that we'll be talking about today is a combination of the actual x86 hardware and how it supports it, but also in some ways, more importantly, a set of conventions that were developed that basically everyone agreed to, and it's known as an ABI. That's why I want to, which stands for Application Binary Interface. So the idea is a document. You can get it online. And it's cited in the book. It's a document that people put together, the initial version, when the first x86-64 machines were first being developed, and specifically for Linux. They said, okay, all Linux programs, all compilers, all the operating system, all the different parts of a system that need to have some common understanding of how to manage the resources on the machine will agree to adhere to this set of rules. And so it goes beyond the actual, what the hardware does, to a set of software standards. And it's called Application Binary Interface because it's particularly the interface at the machine level programming, machine program level. And so that's what we'll be covering today. So people ask sort of, well, who makes up these rules and things? And the point was there was a working group that did this. And there's a separate ABI for Windows. It's similar, but not quite the same. There's a separate ABI for OS X for Apple, and even FreeBSD, a different variant of a Unix-like operating system, has its own ABI that they all share a lot in common, but some of the details differ. So if you think about what goes on in a procedure, even in C, which is a relatively unsophisticated language in many ways, there's a lot going on. And so it's worth breaking down those and thinking about it. One is there's a notion of control. So in my example, I show a procedure P calling a procedure Q. And so when P calls Q, then somehow the program has to jump down and begin executing the lines of code for Q. And then when Q hits its exit point, its return point, somehow it's to get back to P, and not just to any old place in P, but specifically to whatever comes in P right after the call to Q. So somehow we have to record the information about where the return should be to be able to return to the correct place. So that's first of all, passing control to a function and having that function return back to where it should get back to. Second, there's data. How do we get operands to it? So in this particular case, Q is a function that takes a single argument that it calls internally, it calls I. And up here where P is calling it, it's passing some value within P called X. So somehow that data value of X has to be recorded in a form that within Q it will have access to that information. And similarly, when Q wants to return a value back and then P will make use of that value, there has to be some convention of how that data gets communicated back. And then finally, in a function might have some local data that requires allocation of some amount of space. And so where does that space get allocated? How do we make sure it gets allocated properly? And in particular in C, as you know, when a function returns, any local data that it allocated should get deallocated, should be freed up so that we don't sort of start consuming an unbounded amount of storage. So how do we do that? Those are all the sort of different aspects that a procedure call and return have to deal with somehow. And part of the reason for breaking it down into those little segments is in x86-64, one of the clever things they did was to try and reduce the overhead of procedure calls as much as possible. Because as you know, in good programming style, you often write these functions that do a fairly small amount of actual useful stuff. And it's sort of good programming style to do that, especially in a more object-oriented programming style. And so you don't want the overhead, the extra number of steps taken to invoke a procedure and deal with all those aspects to take any more time than it needs to, because it's a fairly critical overhead. So one of the things they do in this is they only do whatever is absolutely needed. So in particular, if no local storage is needed on this for data, then don't allocate it, and therefore don't free it. If you're not passing any values, don't pass them. And in general, sort of how little can you get away with? And that makes it a little bit confusing from a teaching point of view, in that there's no set template that it follows every time. It's sort of, you have to, each case is a special case for how a particular procedure gets implemented. So we'll go through all these parts and see how they happen. And you've already seen little glimpses of them looking at the little fragments of code that we've shown already. So the first one, and sort of the most critical, is how do we pass control to a function? But before we can even talk about that, we have to talk about the stack. So, and you've heard that term, the stack, in various ways. The stack is really not a special memory. It's just a region of the normal memory. Remember, to the programmer's perspective, assembly level programmer's perspective, is memory is just a big array of bytes. And somewhere within that bunch of bytes, we're going to call it the stack. And the stack is used by the program to manage the state associated with the procedures that it calls and as they return. So it's where it passes all these potential information, the control information, data, and allocates local data. And the reason why it can be managed as a stack is because of the nature of the whole idea of procedure calls and returns, that you make a call and you might need some information, but when you return from a call, all that information can be discarded. And so it makes use of that sort of last in, first out allocation principle, meshes very well with this idea of procedure call and return. So in x86, stacks actually start with a very high numbered address, and when they grow, when more data are allocated for the stack, it's done by decrementing the stack pointer. So the stack pointer, as you know, is just a regular register, RSP, and its value is the address of the current top of the stack. And every time you allocate more space on the stack, it does it by decrementing that pointer. Now, just for convention, and I'm not sure why this happens, but this is the way we do it, is we draw stacks upside down so that the term, the top of the stack, is actually shown at the bottom. And just to add to that confusion, and also remember that the addresses go from bottom to top, not from top to bottom. So when you add to the stack, you decrement the stack pointer. Neither of those kind of meshes with your intuition, perhaps, but you just have to get used to it. because we're not going to redry all the slides. So anyways, that's just remember that over and over again. And that's why these arrows show that if we were to enumerate the addresses of these different bytes in the data, they'd be increasing in this direction. And when we add to the stack top is at the bottom of the picture, and we do it by decrementing the stack pointer. So in particular, there's explicit instructions, push and pop, that make use of the stack. And it's often written push Q and pop Q, but that Q is actually an optional suffix on the instruction. So the idea of pushing something onto the stack then is there's some source operand. It could be from register or from memory or an immediate. So this is sort of like a move instruction, but the destination of the move will be toward memory, and the address of the memory is determined by first decrementing the stack pointer and then doing a write. And similarly, the pop instruction reads data from the stack and stores it in the destination, which must be a register for this particular instruction. I think push must be a register too, now that I think of it, or immediate. You can't push from memory to... So pop reads from memory. The address it reads from is given by the current stack pointer. And then it increments the stack pointer by 8. These both work only on 8-byte operands. I'll get to you in a second. And then the result of that is stored in a register. Question?
Is there any difference between like pop and push, or just like doing the three things? Like, is there a difference between like using the pop?
Oh, could you write it as a set of instructions? Yeah, you could actually, except for some weird corner cases, write it out as a set of separate instructions. But it's a common enough thing that it's sort of built in as an operation. Whereas call and return are special. They can't be simulated. So one thing to remember, too, is it's important that in one case you decrement, you do the arithmetic on the stack pointer before you write, because when you first started out, the stack pointer was pointing to whatever was the top element of the stack. We want to create a new top element, so we're going to decrement first and then do the write. Whereas going the other direction, you want to read off the current top of stack element, and then you want to increment the stack pointer to sort of deallocate it. And one thing you'll notice here is when I say deallocate, it's not like I magically erase this or something. All I'm doing is just moving a stack pointer. Whatever was there at the top of the stack is still in memory. It's just no longer considered part of the stack. Okay, so that's the idea of the stack. And the instructions push and pop are to put data on the stack or take it off. But we use the same basic idea for call and return. So let's look at some examples, and there's a lot of stuff up here. But this is a C function called multStore. And then this is the output, slightly cleaned up output from the disassembler of that exact function. And similarly, this is a function called mult2, and this is its disassembled version. And the reason I'm showing this is because I want to make use of the addresses that these instructions are at, that you don't see when you write it in assembly code. So I'm showing it the disassembled version. And the reason all this is up here is because you'll see the function multStore calls a mult2. So I want to show how that works. So, and there's two instructions, and you've seen these in some form. To call a function, you just call it, where you give a label. But keep in mind that these two instructions, and the other is when you're ready to return, you just execute the RET instruction. And keep in mind, though, that these functions don't do the whole business of procedure, call, and return. They just do the control part of it, which, as we saw, is only one of three aspects of a procedure. I'll also mention, you'll see especially in, sometimes it will say REP semicolon RET. And you can pretty much just ignore that. And it's a bit obscure why it's even there. So it's really the same idea. Okay, so let's sort of break this down into its simplest parts. So let's imagine a scenario in which the top of stack is at hex address 120, which is not realistic, by the way. And the program counter, which is called RIP, which is not anything to do with death, is indicating that the current instruction is this at 544, which is this call instruction. And so what would happen with the call instruction is it would do two things. It would, or actually three things. It would decrement the stack pointer, and so subtracting 8 from 120 in hex gives you 118. And it would write the address of the instruction following the call onto the top of the stack. And it's important that it does it, the one following the call, because if that's the instruction I'm going to return, use for my return address, and I want to resume execution in this function at the instruction after the call, not the call itself. Otherwise, you'd have an infinite loop. And it also, this call instruction also embedded in the encoding of the instruction is the destination address of it, which happens to be the starting address of this particular function. So the program counter will be set to that value, and now the processor starts just executing along these instructions. So it did a combination of a jump and a push, and that's why the question was raised earlier. Is a push instruction, could you assemble that out of existing instructions? The answer is yes for push, but not for call. Question back there.
So before you actually go to the function, in like mult store, you would put the address of mult2 into RIP?
No, it did that. RIP, you never explicitly, there aren't instructions that manipulate that directly. It's implicitly part of the call instruction. The call instruction will take, I don't have the actual encoding, but embedded in this call instruction, you see that it's 5 bytes long. I don't show you the byte coding. But embedded in it is the target address. And so it will take that address and use it for the new value of the program counter. So the call does both the pushing of the return pointer and setting the program counter to the new new target for it. Right. So it does both of those things. Question?
Is there anything that's affecting the program counter without using?
I don't think so. With either call or return? If so, it would be really obscure. No, I don't think so. No, so call and return are there might be some weird system instructions that let you do that, but not you'd see in any normal program. Other questions? These are good questions. So okay, so that shows you the control mechanism, how the call works. And then, so now imagine this mult2 chugs along, and it hits its return point, and it hits this ret instruction. By the way, again, retq and ret are the same instruction. And ret will, its purpose is to sort of reverse the effect of a call. It assumes that the top of the stack has an address that you want to jump to. So it will pop that address off the stack, meaning it will increment the stack pointer. Like I said, the value doesn't really disappear from the memory. It just is no longer considered part of the stack. And then it will set the program counter to what it just popped off the stack. And that will cause the program to resume back to where it came from. So you see that sort of clever idea of pushing the address of the next instruction, so when the return comes, it will get it to the point where it should resume execution. Okay, so that's passing control. It's pretty simple. All these things, by the way, and it's just the nature of machine code, every single part of it is pretty simple because it's designed to be executed by the original hardware was fairly simple. It's not anymore, but it's really the basic ideas are. And that we use kind of combinations of instructions to build up all the layers associated with operations like procedure, call, and return. Okay, so passing data. Now, we've already seen a few small examples of passing data. We've seen a couple registers that get used when you're passing arguments to a function. And we've seen the register RAX getting used to return values from a function. And so that's the basic idea. And again, this is all built into this ABI. Defined as a set of conventions, not particularly a part of the hardware. So in particular, the rule is that the first 6 arguments get passed in these particular registers. And you just have to memorize the order of them or have a table handy to look at or something like that because there's no particular logic to it. The return value is returned in register RAX. And by the way, this is all for arguments that are either integers or pointers. I think I've got a little bit on floating point. Those are passed in a separate set of registers. So these are just for, assume now we just are dealing with integer data, pointer data. And then you ask, well, what happens if you have more than 6 arguments to a function, which isn't very common, but it happens. Well, the rule on that is those get put in memory on the stack, and I'll illustrate what I mean by that. So they're passed to the function, and then the function has to retrieve those values off the stack. Back in the bad old days of IA32, by the way, all the arguments got passed on the stack. But now, for the most part, you pass arguments in the registers. And the reason for that is register access is way faster than memory access. Okay, so here's a kind of messy bunch of code, but just to show you how these show up all the time. In the function mult_store has 3 arguments, x, y, and dest. And you can just see within this code that it's making use of registers like RDI. And doesn't show where, and in other places, like mult2 has 2 arguments, and you can see how it's making use of RDI and RSI in the code. So basically, the code is generated under the assumptions that whatever arguments is being passed to it will be passed in that particular set of registers in the particular order they're listed. And the code sort of makes those assumptions. And then similarly, when you have a return value from a function, let's see, mult_store does not have a return value, but mult2 does. And the way it does is it deposits the value into RAX. And then when the return from RAX occurs to mult_store, you see that it assumes now that the mult_store code can assume that register RAX holds the value, the return value, and it can store it in its destination register. And we'll look in a minute why RBX gets used here. We'll cover that in just a little later. But that's the point, that as long as everyone sticks to this common interface standard, then you can even use different compilers to compile code and have them be able to cooperate with each other in terms of passing arguments, returning data. And that's the reason why you want that convention. Yes?
Why is the stack one implemented by 8 bytes
8 bytes because well, first of all, for call and return, it's a 64-bit machine, so all addresses are 64 bits or 8 bytes. But also even the push and the pop instruction only work on 8-byte values. If you said push L, if you tried to write that in 64-bit code, it would come back with a syntax error on it, if you had it in the assembler. So that's different. IA32, there'd be 4-byte values here. Okay, so like I said, you've sort of seen that implicitly in some of the code you've already been looking at, and it's pretty straightforward. To get an example that shows passing arguments, you have to have a function with at least 7 arguments, which is pretty messy to do, so I won't do it, but there's examples in the book. But now, and we'll sort of pick it up, I'll show you also in this later part. And now the third part of it is, again, what if there's some local data that we need to make use of? And so to get that idea across, I have to bring in another concept, which is called the stack frame. And so this is a particular allocation pattern that's used in memory. And as I mentioned earlier, one of the features of calling and returning is you can imagine when you have a nested series of calls to a function, when a particular function is executing, it only needs to reference the data within that function or values that have been passed to it, some of which might be pointers and therefore pointing to other locations in memory. But the point is sort of the rest of the functions in your code, however many they are sort of frozen at that moment. Really, there's only one function executing at any given time. I'm assuming a sort of what you'd call a single-threaded model here. And so we can just allocate on this stack whatever space is required for this particular function. And then when we return from that function, we shouldn't, if it's correctly written, need any of the information associated with that function. It can just sort of disappear forever. And that's why this idea of a stack, you allocate something. If you make more calls, you keep allocating more stuff. But as they return, you kind of back out of the stack and free things up. So the stack discipline is exactly the right, matches well this whole idea of procedure call and return. So each block we use for a particular call then is called the stack frame. And to be sort of more technical, we'll say it's a frame for a particular instance of a procedure, a particular call to a procedure. So just imagine we had a set of functions, one called u, which calls a function called who, and who has multiple calls to another function called mi, and mi is itself is recursive. It calls itself. And so and imagine we had a chain of calls where u calls who calls mi, which calls itself recursively twice. And then we'll exit out of mi and get back to who, and then who will hit its second call to mi, which won't go any further, and that will be it. So this picture here shows this whole history of all these calls that get made. But in terms of the stack, all we need, we'll keep a frame for every sort of procedure that has been called but not yet returned on the stack. And in general, this stack is delimited by 2 pointers. One is the stack pointer, which we're familiar with. And then there's another called the base pointer, which register RBP indicates. But one feature of actually, it's now become a feature of IA32 as well, is that this is an optional pointer. And in particular, the code that we'll see does not use a base pointer except in some very special cases. So this register doesn't really, won't show up in your programs being used in a special way as a frame pointer. It will be used instead just as a regular register. So typically then, the only thing you'll know about the stack pointer, you won't even be able to figure out where the frame is exactly. You'll just know that the top part of the stack is the top frame for the topmost function. And this is all managed by the code itself. And this is the same stack, by the way, in which you're pushing and popping addresses too, and they all kind of get mixed together. So we haven't actually seen any code up till now that has to do any explicit management of the stack, because all our examples were very simple and just made use of the stack only for return addresses. But we'll see some that uses more. But so in general then, imagine that each time you begin a function, some space gets allocated potentially on the stack for its frame. And then, and that frame is indicated by either one pointer only or 2 pointers. And so now as u calls who, then that will create a new stack frame for who. And similarly, when mi gets called, that creates a new stack frame. And as we continue with these recursive calls, we're just adding more stuff to the stack, getting deeper and deeper. And that will keep happening. That's one of the reasons why recursion is a little bit of a risky thing, is that compared to iteration, it keeps requiring more space as you go deeper in the recursion. And in particular, most systems limit the total depth of the stack. And you can have because they're afraid of the sort of infinite loop version of recursion is runaway recursion, where it just keeps trying to push more and more stuff onto the stack. That's an aside. And then as these begin to return, those frames get deallocated, removed from the stack. So part of the nice thing about this is it means that every time if I have multiple calls to mi, because I've gone deep recursively, each one of them will have its own local state that it needs to manage. And again, the whole stack discipline is what makes it work. And what we'll find out in particular is, because of the way this is set up, recursive calls are handled the same way that regular calls are. There's nothing special about them. All the sort of infrastructure required to support recursion is built into this whole stack discipline. So anyways, imagine that all these calls return back to who, and then who would call mi again. And then again, as we exit, we're sort of deallocating these stack frames and getting back to the starting point. Yes, question?
So if RBP is optional, how do you know how much to take?
Oh, so the question was, if RBP is optional, then how does the program know how to do the deallocation? How can it reset the stack back to the right place? And the answer is, and we'll see examples, that the code is compiled so it knows, for example, when it does the allocation, it's going to allocate 16 bytes. And then it knows at the end that it can deallocate at 16 bytes. And it actually brings up a good point. There's sort of an obscure part of the book that goes over this. There's a few special cases where it can't know in advance how much space will be allocated. When it has to allocate an array or a memory buffer of variable size. And then it will actually use the RBP in those cases for exactly that purpose. Okay. And so in general, what the stack frame will look like in one of these machines will be something like this. And you'll see this is the caller, and then this is the stack frame of the the function that got called. So working our way back, if we have to pass more than 6 arguments, the caller will actually use its own stack frame to store those arguments so that they'd be available. And we already saw when you do a call, it will push the return address onto the stack. So before a function even starts, all this information would be on the stack. Now, if there's if we're making use of a base pointer, then we have to have somewhere where to store the old value of the base pointer so that we could fix it back when we return. We won't show any code doing that here, so this is optional. But in general, if there's some local state, like some registers that need to be saved, and we'll see examples of that, or an array that needs to be allocated locally, that will be stored within the stack frame. And there might be some requirement for some extra space in the stack frame for other stuff. In particular, if we're going to pass more than 7 arguments, it needs space somewhere in the stack frame to do it. And what we'll see in typical code is this stack pointer gets decremented pretty soon after the procedure begins, and it gets incremented back just before it returns. And that's how it manages the stack. So let's do some examples. Let's see, I looked at this before. But this is a function. Oh, I think the interesting thing about this function is that it has a pointer being passed to it. So this function takes an argument. One argument is a pointer and another is an integer value. And you can see what it does is it dereferences that pointer to get a value called x. It computes a value y by summing x and the value passed to it. It stores y back at p, but it returns x, the original value of the pointer, not the updated version of the pointer. And you can see that in the code here. Code's pretty short. Remember that in general, RDI will hold the first argument. In this case, it's a pointer. So it will do a read from that pointer, and it will put the value in RAX, which is where the return value should be anyhow. And then it will increment RSI, which has the value called val here initially, and now it has the value of x plus val. And then it will store that in the value pointed to by p, and it will do a return. So you see these 3 instructions do all the different parts of this. And as this shows, in general, I'll show register usage. It's handy, by the way, to document this when you're looking at code. RDI is the first argument. RSI gets used initially, it's val, but now it will be set to y during the call. And similarly, RAX is initially the value, well, it's both what x is here and it's used as the return value. Okay. So let's, the reason to go through all that is to actually show you examples of calling this and how arguments get passed to the function and how it makes use of the stack frame. So now there's a function called callinker. And it's going to create a value called v1 and have to generate a pointer to that. So what that means is v1 can't just stay in a register because you can't create an address of a register. It has to be stored in memory somewhere so that you can create a pointer, an address of it. And where does it store it? Well, it puts it in the stack. So how does it find space on the stack? Well, it allocates it. So the function callinker then, and we'll go through all the different parts of it, but you see that this red code here is generates these 2 instructions.